are going to control it. The people, the government, they are working very much hard. And I wish all the best for you, for USA nation, and all the world, that they will enjoy good health and will be able to defeat this really pandemic, which is really considered to be the first. Nobody was imagining what will happen and how it happens and what we are doing. Anyhow, you will find many people now, they are waiting this actually nice presentation. And we hope that this is the first step, that we will continue in cooperation. And let's hope that we will receive you in Jordan, your second country. You will like it, of course. We are here in the Regional Center for Space Science and Technology Education, and also the EWAS, Arab Union for Astronomy and Space Science. There are actually many organizations in Jordan and the Arab world which they are concerned a lot about space and astronomy. Let me, on behalf of all audience and attendees on the, you see this, let me say, this lecture, welcome you again, and you are welcome. And most of the, just my colleague Ibrahim, he will present very short abstract about your background, which we are proud of it. Thank you, and you are welcome.
Thank you.
Thank you. أخ إبراهيم تفضل إذا بدك تعطي السلايد سريع عن الدكتوراه. بس أخ إبراهيم تسمعني؟
نعم سامعك. ثواني دكتور بس.
إذا بتعرض بس السلايد على السريع.
فقط إذا تعرضون عندك. بس شغله.
إذا بدك أنا ممكن إني أعطيها.
تفضل تفضل.
Okay. So hi everyone. Hi everyone. I will just shortly briefly introduce Anna to most of you. So Anna is an associate professor in MIT, and she works as an astronomer. One of the most important thing about her career that she has received numerous international honors and awards for her discoveries. And she was also like authored for more than 90 papers in various refereed journals, including Nature and other astronomical journals. And the most important thing about her like personality, she always enjoyed to communicate with science and try to give some public lectures. And this is one of her activities to introduce her work to the Arab society. And recently she also published a new paper, a new book, and that is just to try to introduce the stellar archaeology to the wider audience. And it's entitled as the Searching for the Oldest Stars, Ancient Relics from the Early Universe. So welcome you again, and the mic with you.
All right. Thank you so much for this introduction. Maybe one of you can eventually translate my book into Arabic.
Yeah, perhaps I could do that in future.
That would be fun. But yes, let me share my screen so I can tell you my little story. Let's see, I think this should work.
Yeah, it works now.
All right, perfect. I just gotta do one thing. I'll try to, let me just go out of this mode. Yeah. Otherwise, I only see half the slide if I see everyone's face there. But yes, thank you so much for the chance to introduce myself and my work to all of you. I'm happy, of course, to hear that you're all interested in stellar astrophysics and galactic archaeology. And today I want to tell you a little story about a tiny dwarf galaxy that formed a long time ago. And so the short version here of my title is a rare and prolific R-process event that occurred in the ultra-faint dwarf galaxy Reticulum 2. I should just say, my light, if I don't move, it goes dark after a certain while. So I will just, wave my hand and then it gets light again. But yeah, I'm excited to tell you the story because it's really fun. But we need to really start it all from the very beginning. So here's the entire universe on one slide. And we'll start off with the Big Bang on the left. Everything started then some 14 billion years ago. And a few 100 million years later, the very first stars emerged. Now, because they are formed from gas that was devoid of all heavier elements than hydrogen and helium, these stars were very massive. So you make big puffy stars from primordial gas, maybe about 100 solar masses, or at least that order. And of course, with that kind of mass, you have a very short lifetime. And so these stars exploded pretty much instantly within a few million years. And they produced the first heavier elements and they dispersed them into the surrounding medium. And then everything else went from there. So that includes the second and later generations of stars. And so they were formed from gas that contained a sprinkle of metals. And that means that you can make small stars because the gas can clump. You can get to small balls of gas and you end up with subsolar mass stars, and they have really long lifetimes. A 0.6 to 0.8 solar mass star has a lifetime of 15 to 20 billion years. So if you form it really soon after the Big Bang, it would still be around today. And so those are the stars that we are hunting. Then, of course, also more massive stars were formed as part of these early generations, and they produced more metals, more heavy elements, and then star and galaxy formation proceeded up until today. You see my little cartoon here on the right. Now, this is, of course, just a static image. I want to highlight the roles of the role of galaxy formation in this a little bit more, and I have a little video here. What you will see is the formation of a Milky Way type galaxy, so a large galaxy. This is just a dark matter only simulation, but I want you to watch for the red and the yellow dots on the blue and purple background, because those are the sites of the first stars and the first low mass stars, so the second and later generations. And you will see how it all comes together. So I'll play this. And you can just see a few red and yellow dots, and they form along these filaments, and then these filaments kind of merge together to form something bigger in the middle. That's going to be our galaxy, and you can see how the yellow and red dots kind of dance around this and still surround the proto-galaxy that's forming there today, and it kind of zips around. So they're still...
Can you expand the screen, please?
Can you see the video?
Can see, but it is small because I'm looking from, it is like at the corner of the screen.
Okay. All right, I can show it again. So can you see things moving there, the yellow and the red dots?
No, the screen is so small for me. I can't see it. It is at the corner of the screen. It's not expanded like the PowerPoint.
Yeah, it is fairly small. That's true. I apologize for that. I could try to make it bigger. Let me just try this here. Maybe that makes it easier for everyone. I'll just... Is this better?
Yes, sure.
All right. So you can see the red and the yellow dots kind of swirling around the proto-galaxy that's building up in the circle. And so the point here is that even at late times, you can see time and redshift up in the top left corner. We still have red dots swirling around. So these are these earliest star-forming galaxies and star-forming halos. And they continue to bring stars and gas to the Milky Way or to a Milky Way-like galaxy for basically in its entire life. So the reason why I was showing this is to, and I will just say it in words as well, to highlight that it's a very dynamical process, and that the oldest stars, and we'll talk about much of that throughout the remainder of the talk, the oldest stars formed in small dwarf galaxies like these red and yellow dots, and they were then accreted to the Milky Way. So while we are finding them in the Milky Way today, they were actually not born there. And that, you know, by studying these stars in the Milky Way today, we can hence learn about where they might have been forming. So this was just a little introduction. If this was too small and you couldn't see well, it doesn't matter too much for understanding the rest of the talk. But yeah, if there are any visual problems or any questions, feel free to interrupt me. That's not a problem. So let's talk a little bit about chemical evolution. And so we'll pick up off at the big overview slide I had before I showed the movie. If you consider this purple cloud here on this graph to be the primordial gas cloud from which the first and second generation of stars formed, the normal cycle is that, you know, you have a first star, let's say a first star form, it becomes a red giant, it becomes a giant supernovae, the elements get produced they get produced during the lifetime and then get spilled out upon the explosion, and then all this material, this newly created material, gets put back into the reservoir, namely the purple dust cloud there, or gas cloud. And then the next generation of stars forms, and as I said already, the gas then has the sprinkle of heavy elements in it, and then the stars form from that, and then the cycle repeats itself. You have big stars that form, massive stars, you have low mass stars, but with every generation, the gas cloud gets enriched just a little bit more in heavy elements. And so this is what we call chemical evolution, this progressive buildup of elements, heavy elements in the universe. And the natural consequence of that is that early stars that formed soon after the Big Bang, they contain very little of all the heavy elements, whereas younger stars like the Sun, they contain larger amounts. And just as a reminder, although I think you don't really need it, stars are in general made from 75% hydrogen and about 25% helium. So there isn't really much room for any other elements. But we'll look at some numbers in a second. Just to summarize this here, when you want to find the oldest stars, then you have to look for the stars that have the least amount of heavy elements in it. So that's the trick to searching for the oldest stars. And here are some numbers. So the Sun that formed 4.6 billion years ago, so that was the Sun was the product of 8 billion years of chemical evolution. And that brought the level of heavy elements up from 0 to 1.4%. And the oldest stars that we're looking for, so these earliest ones, they have levels of 10 to the minus 4 to 10 to the minus 7%. So it's really, really tiny compared to the Sun. And even though 1.4 is not a lot overall compared to 10 to the minus 4, 10 to the minus 7, that is a lot. So the relative values are what matters. And I'm a spectroscopist, so I wanted to show the exact same thing with spectra. At the top here, you can see the Sun. It has a supposedly very messy spectrum, lots of lines, but it's actually not messy at all, or at least it's not poor data quality. It's every little wiggle in the solar spectrum is an actual line. Because the Sun is so metal rich. So that's what 1.4% looks like. And then if you dial back the clock or you dial